Welcome to Quantum Kinetics Corporation. I am your host, the CEO, and today we're going to talk about black holes and how the black holes in outer space are exactly like the Arc Reactor. So if you're interested, go ahead and stay tuned all the way to the end of the video. So, what is a black hole? A black hole, according to science, is a gigantic massed object that has an intense gravitational flux that pulls in mass, it pulls in electrons, and it also pulls in light. And light can get trapped once it passes the event horizon inside the black hole. Now, here's the interesting thing. According to Einstein's equation, E equals mc squared, mass is the equivalent of light potential stored in a new type of form, which is called mass. This is what happens when you make a gravitational flux using the arc reactor technology with seawater. You get this dense carbon iron oxide material. And guess what? It's extremely magnetic and extremely cold, and it has its own magnetic field dipoles. And the more of this material you make and localize it, the stronger the magnetic field, the stronger the electrostatic field, and thus stronger magnetic/gravitational flux. The primary mechanism of a black hole is a thing called electron capture. What that means essentially is that if a massed object collects an electron, let's say a proton absorbs an electron, when that electron falls into the nucleus, it emits an X-ray, it emits photons, and it changes the proton into a neutron. And that's very important when studying black holes, is because gravitational flux fields do one thing really well: electron capture. Without further ado, let's go ahead and get the arc reactor loaded up on the bench. We're going to show you the arc reactor is going to operate between 2 to 3 electron volts and spit out some amazing X-ray emissions. But before we do that, we have to wait till nighttime and we have to turn off all the lights, because the Pulse Tor SDD is such an amazing detector that it detects the fluorescence in the room and during the day, the light from the sun. So we have to have very special conditions in order for our detector equipment to get a good resolution and a good profile of the arc reactor. So let's go do that.
So right now we're only doing 2 volts or 1.5 volts input, and you can see we're getting pretty much a characteristic 0.7. So this emission spectrum at low power is giving us a good Bremsstrahlung. So we'll go ahead and turn up the voltage in the audio. And we start getting other spectrums as well, as you can see in here. So there's a couple 25s, 10s, 14s. So the arc reactor is doing a very strong Bremsstrahlung right here. And we can change the frequency. You can see here, this blue was the arc reactor on a low test that we just did. The red is an iron 55 sample, which is a calibration sample. You can see here that there's a very strong Bremsstrahlung radiation right here at 0.7 keV and all the way up to about 5 keV right in here. And then this hump right here that you see, this is called the Compton scattering hump, which is characteristic of black holes. A prograde black hole has a lot more radiation here on this region. And we'll show you pictures of what the new star emission looks like, and also from the Chandra Observatory, which is basically an X-ray detector for black holes, that this emission is very similar to the emission of, say, a black hole or a cosmic active nucleus center of a galaxy. So we're going to go ahead and turn it up a little bit more on this next test, because this is just a demo, and we're going to go ahead and raise the volt to about 3 volts, and then we'll have analysis of that. Go ahead and restart the experiment, turn up the arc reactor. All right, great. We'll go ahead and turn down the arc reactor, and we'll go ahead and look at the spectrum a little closer. But there you go. I mean, this is a very good representation of a blackbody radiator, specifically a black hole. And the reason why is because we have this emission peak right here at 0.7 keV. This tells us that the electrons are slowing down. All the electrons near the arc reactor are slowing down, and they're being pulled into the well. This hump right here is essentially our power body curve, which is really where all the real fusion's actually taking place, is between the 1 and the almost 10 keV range. And this emission peak right here, the red, is an iron 55 sample. So you can see the air is actually showing signs of trying to turn into iron as well. And that's just the ambient air. There's no water on this reactor right now. It's just ambient air. This is a Compton scattering hump. This is also very characteristic of a blackbody radiator, and it goes all the way up to 40 keV. And this means that this temperature of this reactor, that's only pulling about 0.7 to 1.1 to 1.9 watts. This reactor is electron volt scale. Its input is around 2.5 volts to 3 volts. And we're getting characteristic X-rays all the way up to about 40 keV, which that is over 400 million degrees. So this is right here. This is about 200 million degrees. This is about 100 million degrees. And we're way over here, okay? And this is where all the fusion, the good fusion, is happening right here. And the beautiful thing about it is we can turn the knob down to the point where this Compton hump actually disappears, and we only have the Bremsstrahlung electrons slowing down, causing nitrogen and oxygen transmutation. And if we want, we can raise the voltage and get this iron peak to go higher. And we can also create aluminum and a bunch of other elements as well. So this is what real transmutation looks like. This is what a gravitational flux looks like. And this is what a black hole also looks like. Okay, so now that we looked at the spectrum, we're going to go ahead and look at something called the raw. And what the raw means is this is the rise time and the drop time of the photon itself. So this is literally the raw data that's being put into or being accepted by the Pulsar SDD. As you can see here, there's a rise time, which would indicate an X-ray, and then there's a drop. Now, this drop, typically X-rays will just go right back to 0. That's a typical positive photon, and that's a very normal thing. But what is not normal is this. This pulse is actually in the negative voltage region. What that tells you is during this pulse renormalization, there's actually a fusion of negative photon pulling in. And if you calculate the distance between this and this, the average is more negative photons in this region throughout the pulse sequence. So what that tells you, ladies and gentlemen, is that this is a Nobel Prize winning device. The Arc Reactor is real, and it induces more negative photons than it does positive photons. And so this one is a 3.228 keV rise time up to here, but then the drop, we don't really know what the drop is. We can go to next, but this computer can only calculate positive photons. And the thing about it is we're actually creating positive and negative photons with this reactor, which means this is gravity. It's pretty amazing. So this, when you look at these peaks and you look at these pulses, what you're looking at essentially is an electron being tugged, released, and then the relaxation is basically what happens when you have electron capture. Electron capture is basically synthetic transmutation. This pulse going down is a negative gravitational flux, also known as a negative differential pressure. This is very important stuff. And another thing that's interesting, if you look after the sequence of pulses, you'll notice that the steady state of the environment is actually below zero reference, which is really interesting because what that means is the pressure, the negative pressure, is still somewhere in the vicinity. So there's still something going on here. Very fascinating. We just found another section of pulses. This is extremely interesting because what you're going to see here is that there's a stair-stepping down effect of the rise time, and it's very interesting because it's almost as if the negative differential pressure, the real world, the positive world, which is here, is having trouble renormalizing to the negative field. It's very interesting. So there's more negative pressure here and less positive pressure here. So this is a void sucking in just like a black hole.
Now that we've seen the arc reactor in action with our X-ray detectors, we can now definitively say that the arc reactor acts exactly the same as a black hole. And you're probably thinking, that's really scary. It's actually totally not scary at all. It's actually exactly how the world works and the entire universe works. Just no one's figured it out yet until now. So Quantum Kinetics is the very first company to ever publicly disclose or show that the arc reactor is a black hole. It also induces safe nuclear fusion, it induces transmutation, and also does synthetic electron capture, which essentially is a Nobel Prize. With advanced technologies, anything's possible, from better living, cleaner health, better propulsion, and also transmutation of radioactive waste. It's all possible using the arc reactor technology. We're so glad that you're coming along for the ride. Go ahead and like, share, and subscribe. Let your friends know because this technology is going to save the world. So welcome aboard. Hey, have you ever wondered how the safe nuclear energy movement was discovered? Well, you can check out our latest book called The Quantum Kinetic Well, Powering the World with Endless Clean Energy. It's a story about an artist who locked himself in a garage for 7 years and discovered safe nuclear energy systems with a box of scraps. The arc reactor is real.